Hello everyone. Today in this video we are going to speak about the second module. Hello everyone. In this video we are going to study about the junction field effect transistors, its construction and its working principle. In the previous video we studied about what is field effect transistor, what are all the kinds of field effect transistor, how much terminal does the field effect transistor has, and we also studied the different kinds of field effect transistors. In this video, we are going to study about the junction field effect transistor operation and its characteristics. Let us have a look into this. We also saw that the field effect transistors are represented the logic symbol of field effect transistor. Now JFET is always operated with the gate source PN junction reverse bias. Reverse biasing means that we are going to connect the source and the gate terminal of the JFET to the negative voltage where in which this is going to produce a depletion region along the PN junction which extends into the N channel and thus increases its resistance by restricting the channel width as shown in the preceding figure. So this is what. So we can observe here whenever these are all the source I have taken an N channel where N is the channel and p-type substrates form a source and the drain. We have the gate terminal. So whenever we want our JFET to work, always it should be gate source voltage should be in the reverse bias condition. So you can have a look at this. Whenever the source, that is this is what is the source terminal, the source and the gate is given to the negative terminal. So I can say my p-type, that is nothing but I am indirectly connecting my p-type substrate to the negative terminal, which is nothing but my reverse bias condition. So always remember your JFET should be in a gate source JFET of the gate source voltage should be reverse bias. Okay, now once we know this, we also came to know that let us first study about the construction of JFET. So this is what is the basic structure of your N-channel JFET junction field effect transistor looks like. The drain is in the upper end and the source is in the lower end of the channel. Two type of P regions are diffused into the N-type material to form a channel, and both the P-type regions are connected to form the gate lead. So this is what you can observe here. Both the P-type channels are connected, P-type regions are connected internally to form the gate leads. So this is about the construction of the N-channel JFET. Now let us look into the working principle of your JFET. Now, when we come for the JFET's operation, we are going to see to that it is nothing but an N channel with this drain at the top and the source at the bottom. If at all we apply the drain to source voltage, which we call it as VDS, to across the terminals, the current starts flowing. The terminal where the majority charge carriers enter the channel, the terminal where the majority charge carriers enter the channel, we call it as source, and the terminal where the minority charge, whether it could be majority or what, leave the channel, we call it as drain. So always drain comes at the top and source comes at the bottom. So wherever the charge enters, we call it as source, and wherever the charge leaves the channel, we call it as drain. So for an N channel electrons or the majority charge carriers, we already know. When we come for the working principle, it basically works on the two principles. That is, first condition works on two conditions. The first condition is making first the gate to source voltage as equal to 0, and the drain to source voltage is varied for some positive value. When I make the VGS, that is, this is what is our VGS, this is my source and this is the gate, I'm going to make the VGS voltage as equal to 0. Once we make our VGS as equal to 0, I'm going to connect the VDS wherein which it makes the gate source voltage to a reverse bias condition. So once I can say it is reverse bias, the PN junctions are reverse bias, then we know a depletion region is formed here, correct? A depletion region is going to be formed. The depletion region width increases with the magnitude of the reverse bias that we are applying, which is the reverse bias voltage that we are applying here, that is nothing but our drain to source voltage, that is VDS. So as and when the VDS is going to increase, the depletion region width is also going to increase, and the potential at the point along the channel depends on the distance of that point from the drain. Points that are close to the drain or at a higher positive potential. So the points that are close to the drain, now we can see there is a depletion region formation across the P region. The points which are very much close to the drain, we call it as, they are more positive, they have the more positive potential relative to the ground, a point close to the source. Both the depletion regions are therefore subjected to greater reverse voltage near the drain. This is the reason why the depletion region starts extending towards the drain. As when more and more positive charge carriers starts depositing over here, so as a result the depletion region starts extending towards the drain. Thus there is a flow of current from the source to the drain, correct? So there is a flow of current from the source to the drain. It is shown as which we call it as the drain current, ID. So now let us vary. Now with this concept, let us go and plot a curve where current versus, that is ID, ID versus VDS. Once we plot a graph of ID versus VDS, now what is going to happen, as we can observe here, initially, the VDS voltage, that is drain to source voltage, is equal to 0. As and when I increase my VDS, I can observe my current ID is also increasing. That is, in this region, I can say my JFET is in the ohmic region. Why it is called ohmic region? Because it accepts the Ohm's law. What does the Ohm's law states? It is nothing but current V is equal to I by R. So I can say as and when I increase my current voltage, the current is also increasing. So I can say this is nothing but my ohmic region where the device is going to accept obey Ohm's law. Now there is a point where even then I am increasing my drains or the drain to source voltage, which is nothing but my reverse voltage. There is a point where the current is going to the current, that is ID current, is going to level off, that is we call it as it is going to get leveled off, or we call it as it is going to be stagnant, where we call it as, or it is going to get saturated, the current. So that we call it as pinch of voltage, the voltage that which we call that voltage, we call it as the pinch of voltage, that is given by VF, pinch of VP, pinch of voltage VP. At this point, further after this also, after reaching the pinch of voltage, even then if I start increasing the drain to source voltage, it will not produce any increase in the current ID. Instead, as VDS increases, both the depletion region starts extending further into the channel, resulting in the narrower channel width, and hence a very high channel resistance is going to be developed across the region. Thus, even though the VDS is more, the resistance of the channel is also high and the current remain relatively constant. Now this region we call it as the pinch off or the saturation region. So IDSS is the maximum drain current, correct? So look into the pointer where it is showing IDSS is the maximum drain current with VGS equal to 0 and VDS is greater than VP, correct? So where the potential, pinch of voltage, as with all the PN junctions, breakdown occurs when the reverse voltage exceeds a certain level called breakdown voltage VB, and VDS exceeds VB. So we can see, you can have a look at the different regions that we can observe here. We have the ohmic region where the JFET is going to behave like an ordinary resistor, that is, it is going to obey the Ohm's law. And pinch off region where the saturation or the amplifier region where my JFET operates as a constant current device, because ID is relatively independent of VDS and IDSS is the drain current with gate shorted to source. And later on, the last region that we are going to observe here is the breakdown region. If VDS is further increased beyond its value corresponding to avalanche breakdown voltage, JFET enters the breakdown region where ID increases to an excessive value. Right? So these are the actions that is going to happen in the or the regions that we can observe. The one more region that we can observe here is the cutoff region. As VGS is made more and more negative, the gate reverse bias increases, which increases the thickness of the depletion region. As negative value of VGS is increased, a stage comes when the two depletion regions touch each other. So as a result, in the N channel, when it is under the condition VGS equal to 0 and VDS greater than VP, I can say VGS off would be equal to minus the pinch off voltage. So this is what is the different regions shown. So I can say this is the ohmic region, this is the pinch off region, and this is where we can expect the breakdown region. And what is the kind of breakdown that is happening here is the avalanche breakdown. Now, JFET operating characteristics in the pinch off voltage. Now when this is going to enter into the pinch off voltage, if VGS equal to 0 and VDS is further increased to a more positive voltage, that is what is shown here, to a further increase to a more positive voltage, then the depletion region gets large. So we can observe here the depletion region is going to get large. It pinches off the channel, so such that it is going to pinch off the N channel. Look into the pointer. As VDS is increased beyond the pinch off voltage VP, the level of ID remains the same. So IDSS is the maximum drain current for a JFET. IDSS is a maximum drain current for a JFET and is defined by the condition when VGS equal to 0 and VDS is greater than the pinch off voltage. Now, let us go for the other condition where my VGS is greater than equal to 0. Here, voltage from gate to source is controlling a controlling voltage of the JFET. As VGS becomes more negative, the depletion region increases. The more negative VGS, the resulting level of ID is reduced. Eventually, when VGS is equal to VP, ID is 0 milliampere and it is turned off. Application of a negative voltage to the gate of a JFET. The level of the VGS that results in ID is equal to 0 milliampere is defined by VGS equal to minus VP, or with VP being a negative voltage for the channel devices and a positive voltage for the P-type JFETs, right? So for the P-type JFETs, we have the peak voltage, that is VGS voltage, as positive, whereas for the N-type JFETs, we have the VGS as equal to minus VP, because we are applying it in the reverse biased condition. So this is what is the operating condition of the N-channel JFETs. N-channel JFET characteristic with IDSS equal to 8 milliampere and VP equal to minus 4 volts. So this is what we said. VGS, we have kept VGS as equal to 0, right? When it is lesser than 0, the condition what we are discussing here is when it is lesser than 0, that is it is more and more negative. So when more and more negative, I can observe the curve here. So it is having the ohmic region, it is having the saturation region. So this is the locus of the pinch off values where we get. So JFET operating characteristics, a voltage controlled resistor, how this is going to act as a voltage controller. The region of the left of pinch off point is called the ohmic region. So the region where to the left of the pinch off region, we call it as the ohmic region or the voltage controlled resistance region. The JFET can be used as a variable resistor where VGS controls the drain resistance RD as VGS becomes more and more negative. That is what is shown in this curve. As VGS is becoming more and more negative, the resistance RD increases, and I can say the current is going to get decreased. As the resistance increases, the current is going to get decreased. Hope this video is useful to you. Thank you for watching.